Hey guys, this is going to be the start of a playlist that's on organic chemistry. So it's going to be a nice review playlist. I might do some lecture videos, but really this is a good starting place if you're taking organic chemistry 1 with this video. This is going to be a good review for the first semester stuff. And also if you're studying for ACS exams in organic chemistry. We're going to start off with nucleophilic substitutions and eliminations. That's going to be the topic of this video. And we'll also have example problems after this video, but I really want to just summarize how you can conceptualize the nucleophilic substitutions. I know it says eliminations. That's going to come later. Eliminations aren't going to be dealt with in this video, but it's like the same rationale for both substitutions and eliminations. So we start with a nucleophile. We have that as the reactant on the far left of this first chemical equation. And we have a nucleophile with a negative charge, and we're reacting that with this substrate, which is an electrophile with a leaving group. So we have our R group, so our alkyl group has a partial positive charge, and then the leaving group has a partial negative charge. Okay, and then the products we have now the alkyl group, the R group, is now bonded to the nucleophile, and then the leaving group is it's written by itself here. So the leaving group now has a full octet on its own. It has a negative charge, whereas in the beginning we had the nucleophile was the chemical species with the negative charge. Okay, so we have an example here. We can say we're going to react a nucleophile, so we can take this hydroxide ion. So we can say, okay, we've got like potassium hydroxide. We put that in a solution with ethyl bromide. Okay, so that's our CH3CH2Br. And this is going to be a primary alkyl halide. So we only have one halogen. We have bromine that is bonded to the carbon, the second carbon. That's why it's an primary alkyl halide. Okay, and after the substitution, we have ethyl alcohol or ethanol, and then we have these bromine ions. Okay, and I've also drawn a graph of the relative energies of molecular orbitals. So when we're thinking about how these reactants actually react in the specific ways that they do, because we know, okay, you've got your chemical equation, the reactants are going to react to make the products, but the specific way that these reactants react and at which carbons and which part of the molecule is reacting is very key to organic chemistry. So a good cheat sheet for being able to predict this is by looking at the relative energies of the molecular orbitals. So I've drawn the sigma one at the bottom, pi orbitals, and then N for lone pairs, right? And those guys are going to be filled. All right, so we're going to say those are filled molecular orbitals. In the unfilled molecular orbitals, we have the p plus, so that's a empty p orbital, and then we have a pi star, which is just an anti-bonding pi orbital, and then we have an anti-bonding sigma orbital. Okay, so the reactions that take place when you're looking at your reactants, the priority goes to the highest occupied molecular orbital reacting with the lowest energy unoccupied molecular orbital. So let's say we have an empty p orbital, and we have a sigma bond, a pi bond, pi bonding electrons, and we have lone pairs on the same molecule. The reaction that will take place that you'll notice is that you'll have the lone pairs reacting with the empty p orbital over, say, the sigma molecular orbitals, or I should say the electrons in the sigma molecular orbital. So we can take a look at this. We can say, all right, this CH3CH2Br, this ethyl bromide, doesn't have an empty p orbital, but what it does have is it has sigma bonds, all right? And on the nucleophile, we have lone pairs. So the lone pairs are going to be reacting with this anti-bonding sigma orbital. And also, if you look at that reactant, it doesn't have an anti-bonding pi molecular orbital too. So it's just going to react. It's going to react with the lone pairs on the oxygen, which is the electrons in the highest occupied molecular orbital are going to react with the electrons on the lowest unoccupied molecular orbital of CH3CH2Br, which is going to be our anti-bonding sigma. So it's the sigma star, okay? Okay, so going a little bit deeper into the topic of substitution reactions, I know I wrote substitution and elimination, but we're just looking at substitutions in this video. So we have the SN2 reaction. So what does SN2 stand for? SN2 stands for S for substitution, the N for nucleophilic, and then the 2 for bimolecular. Okay, so it's a one-step mechanism, even though there's two. So whenever I see the SN2, I just think the opposite of the 2. I think one step. But the 2 is telling you that it's bimolecular. Okay, so it's a one-step mechanism, it's bimolecular, and the rate equation is first order with respect to the alkyl substrate and the nucleophile. Okay, so our rate is going to, the rate equation is going to involve the alkyl substrate and the nucleophile. Okay, so we'll look at that in example problems coming up, but that's just something you have to know now. Okay, so I've drawn a general reaction mechanism for the SN2 here. We have a nucleophile, and it is attacking this carbon on the alkyl substrate, and the X group is leaving. Okay, so we're drawing the electrons going onto the X group, right? And then in the middle we have a transition state. Okay, so in the transition state, the chemical species represented is neither reactants nor products. It's somewhere in between. And then on the right we have the product. So we have the nucleophile now bonded to the position where the X group used to be. Okay, and then we have the X group with its full octet by itself. Okay, and then we're looking at SN1. SN1 stands for substitution nucleophilic unimolecular. Okay, so you could say that it only depends. The SN1 reaction only depends on one of the chemical species. It doesn't depend on both the alkyl substrate and the nucleophile. Okay, so in the SN1 is a two-step reaction. So the first step is the leaving group is leaving, and then in the reactants of, in the products of this first reaction, we have an sp2 hybridized planar molecule. We have a planar carbocation. Okay, we have an ion. It's a carbocation, and it's no longer tetrahedral. The original alkyl substrate was tetrahedral, but this carbocation is sp2 hybridized. It's planar, and it is very reactive. Remember, if we looked at the relative energies of the molecular orbitals, we said that the p orbital, the empty p orbital, p plus, is the most reactive. Okay, so this is a very reactive species. So in our next step, we have this sp2 hybridized carbocation reacting with the nucleophile, and instead of having this transition state where we have something in between the reactants and the products, we have this racemic mixture or racemic mixture. I can't even remember how you pronounce it, but we have racemates, and so that basically tells us what is a racemate or a racemic mixture. That's just saying that we have both stereoisomers. So the first reaction, you have to be careful with the stereochemistry because you only have one stereoisomer as a product. But in the SN2 reaction, since the nucleophile can attack either side of the p orbitals, I should have drawn the p orbitals in there, but there's both of the lobes of the p orbital, the empty p orbital, are exposed, okay, to nucleophilic attack because we have this planar molecule, okay. And it's a planar molecule with an totally empty p orbital. So we end up getting both stereoisomers.